I need to leave early today, so if you don't mind, we're gonna start the class earlier. And I'm recording this for those of you who are not here. We can use the recording data. I have to leave at 4:30 today. So if you don't mind, right? Sure.
Yeah.
I guess you guys do also like to leave the class earlier if possible, right? Yes. Okay, so we are talking about the quiz, the last week's quiz, and the recording that I'm going to upload, I essentially just have the solution in the screen as we talk about it. First problem, let's just review the first problem first again. We have a meteorite that is observed approaching Earth when it is 402,000 kilometers from the center of the Earth with a true anomaly of 150 degrees. So 402,000 kilometers, right? Yes. Theta is 150 degrees. Okay. The speed of the meteorite at that time is 2.23 kilometers per second. 2.23 kilometers per second. Okay. We are asked to find the eccentricity of this trajectory and the altitude at the closest approach, so z of p, and the speed at the closest approach, v of p. We did talk about a couple of different methods for this problem in the previous class. I just want to, get one of them that is a part of my solution. I will also upload the solution on Blackboard. Make sure to remind me of this. And we go from there. So, we can use the energy of the orbit equation, which is v squared divided by 2 divided by mu r. Okay? Velocity is given to us 2.2 to the power squared divided by 2 minus mu, which is 398,600 divided by 402,000 kilometers. If you do the calculations here, the energy of the orbit is going to come out to be 1.4949 kilometers squared per second squared. Yes.
Can you turn the light on? Might be a little easier to see the front.
Sure. Now, for whatever reason, my laptop turns off. I'm recording this. My laptop, the screen shuts off. Okay, so we want to calculate the eccentricity, and we also have to calculate the angular momentum to get to this altitude. Right? To calculate R of P or Z of P, we need to calculate R of P, which is from the orbit equation is h squared divided by mu, 1 divided by 1 cosine of theta. Meaning that to calculate R of P, we definitely need to have h and eccentricity. So what can we do? There's an equation that is we have for angular momentum specifically as a function of the energy of the orbit. 1/2 mu squared divided by epsilon multiplied by 1 minus e squared. Okay. Where does this equation come from? Bonus points. Where did we get this equation from? You go ahead.
Okay, is it combine the orbit equation, the energy equation?
Combine the orbit equation and the energy equation?
And the h equals your tangential velocity times the radius.
Azimuthal velocity.
Yeah.
I mean tangential velocity.
Yeah.
Normally, that's right. Exactly. So this is, what is the orbit equation? H squared divided by mu, 1 plus E cosine of theta. And this is H over R, right? Oh, again, this is not H over R though. This is V. So how would you address this problem?
I did it.
What is it?
I did it a completely different way. I don't remember.
I know. I'm asking how we can use, where did this equation come from? So this equation has H and epsilon energy, and the only place that we actually see this energy of the orbit or the living force of the orbit show up is in the energy equation. So it's a very correct assumption to assume that this equation comes from the energy equation, right? But how did we change the energy equation to give us this equation, right? What do we have here? The only thing we have is energy, eccentricity, and angular momentum. In the energy equation, we have mu. I guess we also have mu. We have R and V that do not appear here. Your heavy bonus points, 2 bonus points for whoever can give me a correct answer. If you're gonna watch the recording later, because this is not what the people who watch the recording are gonna see, they don't really see the board. Referring to the equation that says H, right? Not H squared. Yes, H squared. H squared is equal to 1/2 mu squared divided by epsilon multiplied by 1 minus E squared. Yes.
Do you substitute the orbit equation for the radius in the energy equation, and then you just solve for H squared?
What would you do with velocity?
Replace it with the H squared, H times H divided by R.
That is azimuthal velocity. This is not azimuthal or tangential or normal, whatever you want to call it. This is not the azimuthal velocity. This is general velocity, right?
Replace it with the magnitude.
There is, what is it?
Replace it with the magnitude, and then replace.
So square root of azimuthal plus. So what Allen is saying is that we have to replace it with VR plus V azimuthal squared, V squared. Okay, and what are the equations for these? This is H squared divided by R squared, right? And this is going to be mu divided by H, 1 plus E sine of theta, right? Whole thing is squared. I'm sure this is not going to, this will, but this is not going to give us this equation easily, right? But there's a sine involved, and also the cosine, but I guess it might. Is there any other way to get to this equation? Or how, you have to simplify this to get to the equation, right? You will get the bonus one, but there's also other ways. What is the other way that we can get to the same equation using a simpler approach? Let's increase the stakes. 4 bonus points.
Do I get 4 of those?
You'll get 6. You'll get a total of 6 if you answer. Yeah. But do you have an answer ready?
No.
Okay.
I have an equation B equals square root of U over R. That applies here.
So Connor is saying that we have an equation that says V is equal to square root of mu over R. Does this equation apply here?
That's for circular.
This
right?
is for circular orbits, exactly. So this equation, square root of mu R, does not apply here. This is a very small point. That's actually very important for you guys to know. I'm sure you do know. Just have to think very hard to get to them, right? Let me give you a little bit of, I guess, hint. I'm looking for an equation that does not have any sines and cosines.
V equals mu over h times the square root of v squared minus 1.
What is it?
V infinity equals mu over h.
What is V infinity?
It's a great question.
Who can tell me what the V infinity is?
That's the whole asymptotic. That'd be like the velocity at the asymptote, like as
Excess velocity.
Yeah.
I mean, technically that will be, yes. Yes, exactly. Yeah.
Can you use V equals the square root of 2 mu over R?
Okay, so we have another equation. Does this equation apply here?
That's parabolic.
That is the parabolic velocity, exactly. So this also does not apply here. This is a good review of the whole orbital mechanics, huh? Let's just. I'm looking for other inputs. The rest of you, what do you think? Yes.
What about v equals, or v squared equals v escape squared plus v infinity squared? And substitute v escape with v infinity for their
No. Wait,
Okay.
what is this substitute with?
The v infinity and v escape with their respective formulas.
But then we still have V squared, right?
Yeah, but you can replace v squared to get the energy equation.
Then V escape. How do we? What is the equation for V infinity?
V infinity is mu over h times square root of v squared minus 1.
Can you repeat the equation?
Mu over h times the square root of v squared minus 1.
Times the square root of V squared. So yeah, that is not what I had in mind, but yeah, you can definitely use that. So V infinity is, or V squared is equal to V infinity plus the escape velocity, right? Right?
Yep.
Yes.
So do I get 4 minutes?
This is not what I had in mind. I guess you'll get 2 additional bonus points. But not the 4 that I promised earlier. And we have the equation for this is mu divided by h square root of e squared minus 1, right? This one is a square root of 2 mu over r. What can you tell me about the energy of the orbits?
Greater than
I have that top equation can go to negative mu over 2a. And sub
That doesn't help.
Doesn't help.
No. Because we have this value, right? Breaking this to its component, that is not going to help. Yeah. What can you tell about the energy? What can you tell me about the energy of the orbits? How does it change as your radius and theta changes? What?
Should be constant.
Constant. Exactly. So that this is what I wanted to hear. The energy of the orbit is constant. So if you have the energy right here, right, we can also say energy of the orbit is equal to energy of the orbit at the perigee, which will change this equation to Vp squared, V of the perigee squared minus mu divided by R of perigee. What is V of perigee? H divided by R of perigee squared. And the R of perigee we can calculate using the orbit equation, h squared divided by mu 1 plus e. because theta is 0. So that's the 4 bonus points that none of you got was to tell me this. The energy of the orbit is constant. So this is a very important conclusion because using this, you can calculate the energy of the orbit at any point and use that to calculate angular momentum easily, right? It doesn't change through the orbit. That's the idea, right? Okay, so the point is we are going to get to this equation. This equation is going to relate H to epsilon, which is our energy of the orbit, eccentricity and mu. We have two unknowns, H and E. We can use the orbit equation, the general orbit equation, H squared divided by mu, 1 plus E cosine of theta. We have theta, we have R for this specific point, which means that there will be two unknowns. A system of two unknowns, two equations, is going to give you eccentricity and angular momentum. Right? Does that make sense? Easy. It is, that difficult. Eccentricity we can calculate to be 1.086. Eccentricity 1.086. Angular momentum we can calculate to be what is the angular momentum? 9.5353 10 to the power 9. That's h squared. I have the value for h squared, not h. So 9.53 10 to the power 9. What are the units for these two? What is the unit for eccentricity? What is the unit for h squared? What is the unit for eccentricity? Yes.
Is there a unit?
It is unitless. The unit for eccentricity is no units, right? Exactly. What about the units for angular momentum?
It's still kilometers squared per second.
One thing that you have to, I guess you have to make sure you are aware of that is the fact that this is h squared. So the unit is going to be a kilometer to the fourth divided by second square. Okay, so we have these values using the orbit equation. We can find the altitude of the perigee, z of p plus r of e is equals to h squared divided by mu 1 plus e. We have e 1.086. We have h squared. Whatever the value is. What is the radius of Earth? 6,378. What are the units? Kilometers. Exactly. Thank you. Do not mess up the units. It will cost you in real life and in my exams. Okay. And how do we calculate the velocity of perigee?
That would just be the azimuthal velocity. So.
Velocity of perigee is only the azimuthal velocity, right? Or tangential or normal, whatever you want to call it. Your book calls it azimuthal velocity,
Just h of r.
which is equal to h over r of p, right? And the final value I have for this is 8.51 kilometers per second. Okay. Let's look at problem number 2. The problem, I'm going to read the problem so you can write it in your notes. Problem is telling us an Earth orbiting satellite has a perigee radius of 7,000 kilometers. Let me write it. We have a geocentric satellite, an Earth orbiting satellite, perigee radius of 7,000 kilometers. And apogee radius of 10,000 kilometers. what true anomaly, delta theta, is swept out between T5 hours and T1, I'm sorry, not 5 hours, half an hour. 1.5 hours between these two. And this is hours after the perigee passage. So the beginning of time for us is when you pass the perigee. That is always the case. The same is true for the beginning of anomaly, true anomaly. Okay. And then part B is asking us what's the area swept. So area. How should I solve this? We are given time, we want theta. How should I solve this? You're already receiving bonus for this, by taking the quiz, right? Like I've already received 4 bonuses. What are you waiting for, man? I'm not gonna give a bonus for this. I stand my ground. What is it?
But I don't know.
How should I solve this problem? Those of you who did, again, all of you did take the quiz, right? So how should we solve this problem? I mean, I've solved a couple of example problems using this method. How should I solve this?
I imagine, like, first calculate the period of the orbit. That would be helpful.
So yes. Calculate the period of the orbit using the trial and error, the Newton's method? Sure. In general, whenever you're giving a theta and you're asked to find a time, or vice versa, which is here is the vice versa part, right? What you do is you have to calculate the, like this is an elliptical orbit. We have an RPRA, you don't even need to calculate E, we already know this is an elliptical orbit. In general, you have to calculate, let's say you're given a time, you have to calculate a mean anomaly of the elliptical orbit, and using this you have to calculate an eccentric anomaly of the elliptical orbit, and then you calculate a theta. Right? This is how it's going to go. Right now we are given a t, so we have to calculate the mean anomaly of the orbit. What is the equation for mean anomaly of the orbit? Go back to your notes, tell me what the equation is. Yes.
ME equals 2 pi over t times t.
2 pi over 2 times.
2 pi over
Over mu.
big T.
What is it? 2 pi over
Over the period
2 pi
times time.
time over period. Yes, thank you. There is also another equation, the definition of it. What was the definition of the main anomaly of the orbit?
Kepler's equation. So big E minus eccentricity sine big E.
No. I'm talking about an equation that doesn't have a period and relates it to time.
It's mu squared over x
Mu squared over h cubed,
1 minus e squared,
1 minus
e squared,
e squared.
is to the power of t over 2.
T,
Uh,
what was
that
the rest of it? I
is-
don't remember.
That product is raised to power of t over 2. T, yeah.
Exactly, thank you. These two equations are essentially the same equations. Okay, so you plug t in, you get a mean anomaly of the orbit. What is the next step? What is the relationship between the mean anomaly of the orbit and E, eccentric anomaly,
Kepler's equation.
which is
Mean anomaly equals E minus
E sine s.
eccentricity sine D.
exactly. So, I guess we should have done this first. We should have calculated the eccentricity first, right? How do we calculate eccentricity here?
RA minus RT over RA plus RT.
Exactly. We are given these two. E is going to be RA minus RT divided by RA plus RT. If you do the calculation, your E is going to come out to be 0.17. Okay. And your mean anomaly of the orbit, doesn't really matter which method you use, is going to come out to be for the first one, for half an hour. Right? Let's just make sure. Yes, half an hour. It's going to be 1.45 radians. Okay, so what is the next step? Can I get a value from this equation? Or do I need to do trial and error?
Numerically,
We have to calculate the solution to this problem, to this equation numerically, right? If it was the other way around, if we were given a theta and we were asked to find a time, then we didn't really need to do numerical approximations here, right? Because you just plug E in and that would give you the final solution. How do we do the numerical approximation? The first thing you want to do is to form a function, f. Essentially, you have to move everything to one side. So E minus E sine of E minus mean anomaly of the orbit. And we want to find the roots of this function, essentially, right? You have to make a guess. You have to make it like your second, the answer to solution. The solution to this approximation is your guess minus the value at that point, the value of the function at that specific point for that specific guess divided by the value of the derivative of the function. We already have the equation. So trial and error, you have to do this as much as long as until you meet the residual criteria. But for this problem, we only need to do it once. Here, if you do it, I guess once, your E is going to come out to be 4.2 radians. What is the next step? Next step is to find the theta. What is the relationship between E and theta? What do we have in our lecture notes? What is the relationship between E and theta?
E equals 2 inverse tangent times the square root of 1 minus E divided by 1 plus E times tangent of theta.
E is equal to, let me actually write it as a function of theta. But that is a more common one. So we can say tangent of theta over 2 is equals to square root of 1 plus E divided by 1 minus E tangent of E divided by 2. Right? Yes. You can rearrange the whole thing to give a function of E, function for E that calculates E. So you have E, just plug it in, you find theta. The value of theta that you're going to find is going to be 103 degrees for this half hour after perigee. And for a 1.5 hour, it's going to be 120 degrees, 23 degrees, I think. Let's see. 231, I'm sorry. So what is delta T? Delta T is just a difference of the two. Delta theta, I'm sorry, not delta T. Delta theta is the difference between the two. Okay. Well, how can I find the area that is swept through this process? How can I find the area?
I know that's calculated law, treat the equation.
So the idea is area is related to the angular momentum, right? The rate of area that is swept throughout an orbit is constant, first of all, and is related to angular momentum. We can show that the area that is swept through time, delta or dt, dA dt is equals to angular momentum divided by 2. So we have to calculate the angular momentum here, first of all. Okay. How do we calculate the angular momentum?
Use the perigee radius.
What is it?
Use RP. RP is
Just
what-
exactly. Then you find the angular momentum. That's it. Do you have any questions? No. Okay. Let's move on to the lecture. We're going to do a very short lecture. And we'll just finish the class soon. We're going to talk about orbital maneuvers, and we're essentially going to talk about how to transfer an orbit. That's the idea. Interplanetary flight. We're going to talk about, we'll have a little bit of introduction, then we're going to move on to talk about impulsive maneuvers, and then Hammond transfers, bioelectric Hammond transfers, and non-Hammond transfer if we have time. I think we have enough time because we are moving fast enough. Non-Hammond transfers in general. Okay, first of all, orbital maneuvers are going to transfer a spacecraft from one orbit to another. How can we make this transfer happen?
Is you use the orbit's momentum to kind of like slingshot you.
You'd use the orbit's energy and momentum. So what was your name?
Jacob.
Jacob. I'm sorry. What Jacob is saying is that let's just use the orbit's energy to transfer its orbit. Is this something we can do? Is it possible to use the orbit's energy to transfer the orbit? No. Why not? You expect a bonus for all of your answers. I think you're already at 10, aren't you?
I don't think so.
For this, I'm sure for this course you have earned a lot of bonuses. And I have not included the bonuses that you have submitted. Right? Yes, that will be added, that will be done at the end of the semester. So no, why not? Yes.
You said earlier that energy was constant.
Energy of an orbit is constant. So, what will happen to our orbit if we change the energy of the orbit?
Just drop into lower altitude.
It will be a different orbit, right? Or it will become a trajectory. We want to go from one orbit to another orbit, which essentially means that we have to change the energy of the spacecraft, right? Okay. How do we change the energy of the spacecraft?
Using propulsion more thrust.
Using the rockets. Exactly. That's it. So you have to generate thrust to change the orbit. That's the idea. So the idea is, let's say you have a satellite orbiting around the Earth. You want to send it to the Mars orbit, right? you are going to take advantage of the fact that the Earth and Mars are orbiting around the sun. So essentially you're going to increase the energy of your satellite to escape the orbit of the planet Earth, first of all, and then to get enough energy to go to this to Mars, right? But let's say your satellite arrives at Mars. Then what?
Then you'd still be in like a solar orbit until you boost backwards to essentially capture.
Exactly. So you have to change the energy of your orbit again. If you don't do that, you are going to orbit around the sun. You are not going to be orbiting with Mars around the sun. That's the idea. So the point is, we have to have impulsive maneuvers. And what do you mean by impulsive maneuvers? We have to fire the rockets for a little bit to change the velocity, to change the carry energy, to go to a different orbit, right? And that's what an impulsive maneuver is. The idea is you have to keep in mind that this is just a very sudden firing of the rockets, right? So we just assume that it happens instantly without any position change. So at one point, you are not on a circular orbit around the Earth anymore, for example. You're just on an elliptical orbit around the sun, right? To go to Mars, right? And the amount of specific impulse for these impulsive maneuvers is related to the changes in mass divided by mass is equals to 1 minus e to the power the velocity change, the velocity jump divided by the specific impulse multiplied by g naught. But our goal here in orbital mechanics is to calculate not the specific impulse, but that's a propulsion thing, right? Not even the changes in mass, but that is also a propulsion thing. Our goal here is to find this delta V needed to be put on the new orbit, right? And to get to the original orbit, the target orbit. So again, let's say this is a big picture view of things. So we are not talking about escaping the Earth orbit, right? We're just going to look at our satellite as orbiting with Earth around the sun, and we want to move it to the Mars's orbits around the sun, right? We're gonna go from Earth to Mars. Okay, so what do we need to do? At one point, you have to increase the energy to be put on an elliptical orbit, which perigee radius is the distance between Earth and Sun, and apogee radius, or apoapsis radius, it's not apogee radius anymore. Apoapsis radius is the distance between Mars and Sun. Okay? So you increase your delta V, you have to create a delta V. The new velocity has to be elliptical orbit, which perhaps this is the distance between Earth and Sun. Apoapsis is the distance between Mars and Sun. This is also true for all planets, not Earth and Mars. And when you arrive at Mars, you have to change your velocity again to be put in Mars's orbit, an orbit around the Sun, essentially with Mars. Does it make sense? So two impulsive maneuvers to go from one planet to another planet, to transfer orbits, right? One is to go from the first circular orbit to the second one. And the other one is to stay in the third orbit. Okay, how can we find the delta V of these orbits? Yes?
The difference in energy, we just use the energy.
The different, we can use the difference in energy between the two. We can do. There are a lot of things we can do. The point is, you have to calculate the velocity of the orbit of the first orbit. Then you have to calculate the velocity of the orbit at the jump location. Let's call it the jump location. For the second orbit, this is going to be your first delta V. Second delta V is going to be the velocity of the orbit as at the Mars location, wherever you want to go to. of the second orbit and the velocity of the third orbit, that's your target orbit. Okay? So 2 delta V's. And the total delta V is going to be just these two delta V's added together. Okay? But so we are going to start by start talking about orbit transfers by talking about Harman transfers. Harman transfers are the most energy efficient transfers that you are going to come across. Why is this the case? Or like, how does the Harman transfers work? Harman transfers go from the preapsis of one orbit to the apoapsis of the other orbit, right? So the point is your transfer orbits, the first jump point of the transfer orbit is at the preapsis of the transfer orbit, second orbit. And the second jump location is at the apoapsis of the target orbits. This kind of transfer is called the Harman transfer. This is the most efficient type of transfer. Why?
I know, I believe it's called like the Oberst effect, where propulsion it's most efficient to change your altitude if you burn up energy.
Well, why do you think that is the case? Yes.
All you need to do is add a tangential velocity that you're perfectly perpendicular to.
Exactly. So the velocity you need to add is just in the tangential direction, right? And there is no direction change. You just have to change the magnitude of velocity at that instant, right? Because the direction at the preapsis for both and apoapsis for both orbits is going to be the same direction, right? Does that make sense? So Harman transfers. Let's stop here. We are going to continue talking about the Harman transfers and the rest of this on Monday. I think we're going to finish this. I'm sure we're going to finish this on Monday. And on Wednesday, we are going to talk about the exam, which is going to be on Monday, after, like the Monday in 2 weeks. And yeah, do you have any questions?